one you gotta turn
Hey,
in.
Kenny, you might need,
Give you a new one?
yeah. Because I was reorganizing my binder.
Sure.
I actually was.
Oh yeah, Mr. Can we turn it into you?
You do? Then turn it into me later as you head to lunch something. Alright, so please notice, why do I have all of this in green?
Because we've already covered it.
We've already, like this foundation for means, we've done almost every single thing here. The only thing we haven't done is standard error for X bar, but that should make sense because we've done something similar. We'll come back to it. And then match pairs design. That's the only new thing, really. And I think we did a match pairs design actually back in study design, didn't we? Yeah, we talked about the beard, right? So like one treatment on one side of my beard and the other treatment on the other side of the beard, as opposed to my beard versus Coach McKinney's beard, right? Match pairs blocking on me. That match pairs idea is when we block on me because no one's more similar to me than me. Okay? And so match pairs design is actually going to come back up, so I should have made that green as well, but we're going to apply that. Okay, this is all the new stuff though, okay? T distributions, standard error and a sample mean, degrees of freedom, and a T critical value. But we're still going to use the 4C method for inference and all this, and all that. So you'll notice, what critical value are we not using? We used Z last time, didn't we? Now we're going to use something called a T. And we need to understand what a T is and learn what it is and why it's necessary, but don't sweat that yet, okay? So, how much does an Oreo weigh? According to the package, 3 Oreo cookies should weigh 34 grams, which means the average weight of an Oreo cookie is 11.33 grams. A skeptical AP Stats student wanted to find out if this was true. So she selected a random sample of 30 cookies. The mean weight of the sample was 11.19 grams, with a standard deviation of S equals 0.08. What are we going to do?
Construct the confidence interval.
Construct and interpret a confidence interval. So 4C method of inference. Alright, so I want you those to go ahead and work through this with your small groups. You can do vertical surfaces or not. You should be able to work through number 7. So I'm going to give you all 10 to maybe 15 minutes to work through number 7 together.
The true meaning of all Oreos.
Yes. Yeah, sorry, I forgot about that. I had community group last night. I did not. Of this. All right. So, really quick reminder, okay? What is P? Thank you. Population proportion.
That's what I said.
Okay? No, it's not. Okay, and so this is an aside, but it's going to tie in. What is the point estimate for the population proportion P? P hat. That statistic is a point estimate. Okay? Now, we're not looking at a population proportion, we're looking at a population mean, which is mu. What are we going to use to estimate mu, the true mean? X bar. And so, I will point out, number one, when it just says what is the point estimate for the true mean, they're just asking for X bar. They're not asking for the statistic yet, they're just asking, hey, what estimates mu? X bar estimates mu. Okay, that's what they're asking at number 1. Okay, population, sample, parameter, statistic, y'all did great with that. Okay, so population was all the Oreos in the world. The sample was our 30 Oreos. The parameter, remember that's what we're trying to estimate, is the true mean weight of all Oreos. That was really well done in green up here. And then the statistic is the 11.19. Ooh, there's one thing that's missing here. Does anyone know? The units. The units. 11.19 what?
Pounds.
Did you just say pounds? You think an Oreo is 11 pounds?
Yes.
What Oreos you eating?
I don't eat Oreos.
Well, that's a lie. Sounds like a broken inside if you don't eat Oreos.
I'll order.
Almost nothing better than dunking an Oreo in a cup of milk. Let it get nice and soggy. Oh,
Make sure Kitty don't make me hungry, okay?
so good. All right.
Can we have Oreos?
I will try to stop by the store.
Yes.
Was the sample a random sample?
Yes.
Yes.
Yes, it was. How do we know that?
A random sample of 30 cookies.
Okay, so random sample was what? What's stated? Don't just say random check on the AP exam, don't just say random check on your test tomorrow, random sample was stated, or random assignment if it's random assignment, okay? You're a state
What's
of
the,
annoyance.
what's the?
Aha.
Why is this important? So we can make an
Uneducated guess.
not educated guess.
An unbiased.
An unbiased, a reduced bias.
Okay, so reduced bias, but why does reducing bias matter?
Inference of the population.
An inference,
Ian, that was disgusting.
I don't wanna know.
I think we can.
You are disgusting.
Okay, don't forget, actually put that context in there, but it's an inference about the population. Questions, comments, concerns through number 3.
You should see the things he does.
Well, no.
No.
Yes, ma'am.
For your statistic, can I just put X bar is equal to 11.1?
Actually, I would have. Here, you're talking about?
Yeah,
Yeah, I would have put that as my statistic.
okay, you wouldn't have to put any more? Okay.
Because you already defined the context over here.
Is the statistic, is the statistic not also 0.0?
There is a statistic, but if we're trying to estimate the true mean, the statistic to estimate the parameter is X bar. Yeah, you could definitely include S is equal to 0.08. That is a statistic.
Oh, and 30.
Wait, what happened?
No.
Kind of, yeah. Really, that's the one that matters though. Okay. Number 4, formula for calculating standard deviation of the sampling distribution. Now, to settle a little bit of debate, technically what number 4 is asking for is this. The true standard deviation of sample means is equal to what?
Standard deviation divided by square root of the sample size.
For everyone who went ahead and jumped here, guess what? That is important because what do I not have from this formula?
Standard deviation.
Which standard
Sigma.
deviation?
The true.
Sigma, the true standard deviation, right? I don't have the true standard deviation, so can I even use this formula?
No.
No, but notice that's what number 6 is about. Okay, so that is the true standard deviation of the sampling distribution of X bar. Now, what condition must be met?
Central.
No.
10%.
No, that was.
10%.
Are you serious?
No, I wrote it down, but they didn't go down. So-
What is the central limit for? That's so the sampling distribution is
Approximately normal.
approximately normal. Remember, your central limit theorem is all about approximate normality, okay?
I thought.
This is the condition for my standard deviation formula.
Why didn't you just talk about it then? You were like, it is sufficiently large.
I didn't pay attention to which question you were writing this for.
Straight
Straight up.
Are large,
Notice your answer goes to number 7. All right. What's your question?
are large counts and central limit theorem for approximately?
So large counts is only for what? And we need to pay attention to that. Large counts, remember, is n times p. If you don't have a proportion, can you do large counts?
No.
No, that is a common mistake that we gotta make sure we get right now. Large counts is only for proportions. Large counts is this. Do we use large counts then with means?
No.
No, because means don't have a proportion. So good question. Make sure you hold on to that. Do not use large counts here. Okay. So we got 10% condition. Has it been met? Is it safe to assume 30 is less than 10% of all Oreos?
Yeah.
100%.
There are more than 300 Oreos in existence.
Say it again.
There are more than 300.
100%. I've probably eaten way more than 300 Oreos. I won't tell you the time frame that I am talking about.
Call it?
Like, Mr. Thing, do you ever eat Oreos and M&M's in the same day?
No.
Why do you know about Oreos? You don't like them.
You do some. I don't know about them.
Oh. Number 6. The formula for standard deviation, we don't know the value of sigma, so we will use S instead. So we don't know sigma x bar, we know S sub x bar, which is S.
Divided by standard root of n.
Okay, that's it. So 0.08 Is that what it was?
Okay.
Divided by the square root of,
30.
so what is that gonna be about?
0.
0 point, it's right there.
146.
Right? This is approximately S sub, or sigma sub x bar. So notice, this is S x bar, that is the standard error. So when we use S, that's the standard error. Sigma is the true standard deviation. Now here's the question. Would it be appropriate to use a normal distribution for the sampling distribution?
Yes.
Yes, because you're using the what?
Me.
The z-score.
It is sufficiently large for the,
Chicken lettuce tomato.
n equals 30, which is sufficiently large for what? Central limit theorem. So, sorry that I did not catch y'all on that earlier, but yes, 10% condition is for the standard deviation
That's okay, I'll
formula.
let it pass.
The central limit theorem is what we would use here. Okay? Now, I do need you to remember, do you always need the central limit theorem?
No,
Probably not.
You only need the central limit theorem when the population is what?
not on that.
Not saying it.
So, not normal, not symmetric, it's skewed, right? So remember how we had our pennies down here?
Yeah.
Okay?
Yes.
So remember how we had pennies? And with those pennies, that was a very skewed distribution. But when my sample size got large enough, was the sampling distribution still skewed?
No.
No, it was approximately.
Wow.
Okay, so remember, if it was already normal though, you don't have to worry about central limit theorem. Okay, so we have a sufficiently large, sufficiently large for the central limit theorem. So the sampling distribution is approximately normal. Okay, so I'm going to show you something that is not a part of. No, I don't know who set that off.
Time for fruit
That must have been my Algebra 2 students. Okay, so let's say that we wanted to do, yeah, see I don't like where they jump here. Let's say we wanted to do a 95% confidence interval,
Okay.
okay? What would we do based on what we already know for that confidence interval?
Well, don't we need a,
You need to take the statistic.
So we need our statistic, plus or minus
Critical value.
a critical value.
which is
Times.
Well, no, we haven't learned it yet. Times my standard error. And what is the standard error?
0.0146.
Well, S divided by
My bad, excuse me.
root n. So, let's say we don't, I know you know that we need a t because I told you we need a t, right?
Okay.
But if we don't know anything about t, what are we going to use for our critical value?
Z.
We're going to use z, okay? So x bar was 11.19 plus or minus, what's the z for 95%?
Oh, 1.6, 1.96.
1.96 times the standard error of 0.0146. Now I probably would have written that as 0.08 divided by square root of 30, but let's look at this statlet. And it was not working yesterday, so I'm praying it works today. All right,
Close that. You're making the
come on, statlet. Haha. Okay. Okay. So here we go. So we're going to do a z distribution with sigma, okay? Our sample size is 30.
0.5.
The population is normal. And 95% confidence interval.
Ian is
Start just as disgusting.
Ian, you vile human.
Wait, why are you not letting me? Okay. So, what we're going to do, okay, right here.
Where's the key now?
Okay, hold on. Okay, right here. Mu equals 10, sigma equals 2. We're going to use what they already have here to understand a confidence interval a little bit better. So, we are trying to estimate our, create a confidence interval from this data here. And so notice it generated this. There's my sample data, sample size 30, and so it created an interval. Did that interval capture the parameter of 10?
Yes.
It definitely did, right? Now, I'm gonna go ahead and have it do 100. About how many of my new intervals should capture that parameter? 95%, right? Could it be a little off?
Yeah, sampling variability.
Sampling variability, okay? So what percent caught?
Real juicy, real
92.
92%, okay, let's do it again.
96.
Now that time was a little bit higher, right? Because of
Sampling
sampling
variability.
variability. So in the long run, what percent do we expect to see for our capture rate?
95.
Is that what I'm seeing?
Yes, Bill takes you on that.
Okay, now, that was doing, coming back up here, Z distribution with sigma, but do we have sigma? No, we don't. So we need to do, let's do Z with SX, the standard error. This time, okay, so I'm gonna clear, reset everything. Okay. Alright, still have a mean of 10, sigma is still 2, sample size of 30, 95% interval, now a Z distribution with S. And go. Did I capture the parameter that time?
Yeah.
Alright, now let's do 100. That time I captured 96 times, sweet. That time only 93. Does anyone see a problem with our intervals? Yeah, I was say, what's my capture rate right now? 94%. Say again.
Why won't you be 95?
I know. So look, I need you to see something right here. Anyone see anything interesting about these intervals?
Very far.
Look at like this red one that missed versus this green one that missed. It's shorter. Some of these intervals are actually shorter than others, which is part of the reason. Well, here's the thing. When we did these intervals, how did we calculate it? Or how did we calculate our standard error? We used S divided by root n. That S is based on the sample. Does the standard deviation of our sample change?
Yes.
Yes. Guys, the standard deviation of our sample is going to change. Sometimes we have a bigger standard deviation. Sometimes we have a smaller standard deviation. So if we use a Z critical value with this S, we're going to have the wrong capture rate. Let me say that one more time. If you use Z, so if you use Z with S, then you will have the wrong capture rate. And that is because, what can S do? S can change. Depending on the sample, that S value will be different, making our interval wider or narrower. If your sample has a small standard deviation, your interval is going to be narrower. So what do we have to do? You have to not just use another letter. What do I need to do to those intervals to make it have the right capture rate? I have to make them be long enough. I want y'all to understand that. That's the idea behind a t-distribution. The z here is not going to make my intervals wide enough. So I need to make them a little bit what? A little bit wider, a little bit longer. So your t, t will always be greater than z.
I'm having data we might not.
So this is a little larger to make a correct capture rate. A little larger to, let's say, so if the critical value is a little bit bigger, what else is that going to make bigger?
Huh? Oh.
If the critical value is a little bit bigger, what else is that going to make bigger?
The
The what? Yeah, the margin of error, right? It's not going to change the standard error, but if we make the critical value a little larger, we're going to make the margin of error larger, and get the correct capture rate. I need you to understand, right? Because what is, by the way, what does that margin of error account for? You need to know this for your test.
The margin of error counts for sampling variability.
Margin of error accounts for sampling variability, but we have a problem right now. Not only do we have sampling variability in the mean, we also have sampling variability in
The standard deviation.
the standard deviation. So we have to account for that extra sampling variability. Okay? That's the idea, is that this t is going to account for that extra sampling variability. Alright, so let me reset this. Notice, again, some of those intervals are wider than others because of S. Alright, I'm going to reset everything. But now I'm going to use t. And go. So notice in this case, notice how the S is 2.379, right? So there's that standard deviation. So I'm not going to do 100 yet. I'm going to keep it at 1. And so we captured, all right? Notice this time, did I get a different standard deviation? Yeah, right? Sometimes that standard deviation is going to be larger, sometimes it's going to be smaller, and so we have to account for that. So one more. Did we get another different standard deviation? Yeah. So we have to account for that. Now I'm going to do 100. Okay, 97% capture rate, 91% overall, or no, 95% now. Huh, what's my capture rate now? Pretty darn close to what? 95. And if I keep going for infinity, what's that capture rate going to approach? 95%. So guys, we have to use something other than Z. We have to use T to make it a little bit larger. Okay, so that's what's going to happen here. We're going to use a T critical value instead of a Z critical value to make our margin of error larger. What's up? What is T?
Yeah.
I'm about to show you. Yeah. So I just want to establish this. We can't use Z because it'll have the wrong capture rate. We have to use T because it makes the margin of error a little bit larger. And let's look at the sheet to see where that comes up. Let's see here. First off, all right, so when finding the margin of error for a confidence interval, we use Z star. For a mean, what are we going to use?
T star.
Why?
Because it makes the margin of error larger.
Right. So two things I will point out. This would be a great place to have this first note. Z, you will have the wrong capture rate because S can change. So what do we got to do? We got to use T to make it a little bit larger to make the margin of error larger and get the correct capture rate. So T is going to give us the correct capture rate. Fun fact, this is the only thing that's different about means and proportions.
Other than like LCC and L.
Well, in large counts condition and central limit theorem, yeah.
Well, here it is.
I wish I knew what you said.
Or you don't want to hear that.
You don't want to hear that.
You don't want to hear that.
Just make it funny. Never mind, I'm scared.
Don't tell them.
Okay.
I mean, I can tell you.
Nope, I'm out. Okay, so before we look at this, so I'm going to show you the table. Hey Ian, you remember that table that you wanted?
Yeah.
Yeah, same. Okay? Hole punch it later. Please remember this table. What type of table was this, or what type of distribution was it?
Z stars.
Nope.
It's a normal table.
Second and Charles.
What's it start with? Don't spoil. What's it start with?
The Z's.
It's not Z.
What's it start with? Don't spoil.
T.
Look at it. What's it say at the top?
Confidence level.
Distribution of critical value.
Never mind.
Oh, table B.
Table B, which says
T distribution.
T distribution. Can you make sure everyone gets one of these? So guys, this is your T distribution chart. I will point out, you can also use a calculator. Say again.
You need another page.
I only gave you 2.
Yeah, it doesn't know how to use exactly.
There you go, Talia.
Alright, I know.
Who did I not give?
Me.
Hey guys.
Okay, I'm trying to do that.
All right, so I'm going to draw a picture so that you can see this a little bit more clearly. So what is happening is this. So let's say that this is my normal distribution right here. We good with that?
Yes.
The area underneath that thing is what? It's 1. But we just said that the T distribution is going to have slightly larger values, right? So it's going to be more what? More spread out. Now, it's not going to be as tall because the area is still going to be 1. So this isn't going to be exact. This is just an estimate. But this may be, so let's say this. This purple right here would be a T, maybe with the degrees of freedom. I'm going to explain what degrees of freedom are in a second. The degrees of freedom of like 4. Okay? I'll explain what the degrees of freedom are. Okay? This green right here okay? This green here would be a T with the degrees of freedom of maybe 10. Don't sweat it yet. Okay? This orange here the orange here will be a T with a degrees of freedom equal to, I'm just going to make something up, let's say 30. So what's happening to my T as the degrees of freedom increases?
It gets taller.
It doesn't just get taller, it gets what? It gets less spread out. Notice it's approaching the what?
The true mean.
It's approaching the Z. We need to recognize that. I heard someone saying that, a couple of them saying that. Notice, isn't that orange getting closer to the pink Z distribution?
Yes.
Okay? So, as the degrees of freedom, which I should probably write that out. Oh, do you see that somewhere? What do you see that?
Oh, it's on the side.
Oh! So as degrees of freedom, increases, the T distribution approaches what? Z. As the degrees of freedom increases, that T distribution is approaching the Z. I want you to think about it this way. Well, actually, does anyone know what that degrees of freedom connects to, by the way?
Is it a spread? Standard deviation? Sample size? The standard deviation?
Sample size.
Degrees of freedom connects to sample size.
Good
Okay?
job, you.
How did you know that, by the way?
It will never
Because
be.
as sample size increases, distributions become more normal.
I want y'all to understand that and hear that. That's actually really good reasoning. Guys, as sample size increases, doesn't our distribution become more normal or it approaches normality, right? There's another thing I will point out. Number 9. What does it say degrees of freedom is?
N minus 1.
What do you think N is?
Number.
Sample size. Yeah. So degrees of freedom is just sample size minus 1. Okay? So, as the degrees of freedom increases, or as the sample size increases, the T distribution approaches Z. Okay? Or the Z distribution, I should say. So, what t is needed for this confidence interval? What confidence level did we use?
Wouldn't it be 29?
What confidence level?
Oh,
95% confidence.
1.96.
And now it's 1.96 if we were using z, right?
Oh.
But what's my degrees of freedom here?
29.
The degrees of freedom would be
29.
29. What was our sample size? 30. So 30 minus 1 is 29, okay?
2.045.
So this is what we'll end, yeah. T, so looking on the chart, degrees of freedom of 29, confidence level of 95, gives me 2.045.
Micro head out.
Alright, head on out. But notice, is that bigger or smaller than 1.96?
Bigger.
Bigger.
Because we needed a slightly larger value.
So I'll be. Let's start with B.
You might want to say bye, Mr. Anderson. I'm guessing that he's about to leave.
No, I was gonna say.
Oh, you're gonna say?
I have to for the one time.
Yes.
For the what?
I have to for the last day.
Oh,
You know, I'm just.
But I was saying, don't you? Alright, so getting back to where we left off. So, the T of 2.045, right? It's just on that sheet. I do want to show you how to use the calculator quickly to do it. Any guesses how we're going to find our T using the calculator?
The menu.
Okay, so go ahead and pick up your calculator.
The T
Is this not Miss Granberry's calculator?
One of them might be.
It says number 2 on the top.
Yeah, that'd be Miss Cranberry.
Are we gonna deliver it?
No,
Okay, well.
she let me borrow it because it wasn't working and then I fixed
Wait,
it.
what do you mean?
So, menu, statistics, and where? Or probability.
Stat test.
No, dude, we just want a T value. We're not doing a whole test.
Confidence.
No, we're not doing a confidence interval.
1. Stat calculation.
Distribution. So remember, when I wanted Z,
4.
hey guys, when I wanted Z, didn't I just go to
It's
distributions?
CDF.
So do I need TCDF or do I need
A
inverse?
PDF.
Wait, what?
Inverse, probably.
I was saying, remember to get a Z, didn't we have to take the area and do the inverse normal?
This is starting to make me busy.
To find the T, I'm gonna have to do an inverse T. So go to number 6. Alright, 95% confidence level. What's my area?
0.95.
0.95.
Nope.
It's
0.05.
0.05.
0.05. So, 0.025, or remember you could use the 0.975. So remember, the confidence, when you're doing the inverse, it's always the area to the left. So put a 0.025 in there, and what's our degrees of freedom?
29.
29.
Negative 2.04.
Because remember, the sample size was 30. Degrees of freedom is n minus 1. Yep. Is that the same T that we saw on the table?
Yes.
Well, it's negative instead of positive, but if you did 0.975, it would be the correct T. I just showed y'all how to find the T using the calculator. We would just put it positive, right?
Mr. Can you please?
Lorelai.
Can you please
We need.
tell me what we're pressing? We're pressing me.
Okay. How did you find Z critical values? Did you go to either probability or statistics?
Yeah.
Okay. Distributions.
Mm-hmm.
And once you to do a Z. Yes.
Okay.
Okay. Inverse T. You just have to have your area and the degrees of freedom. Now I will point out, I probably just use the table. Living in the 21st century, the finding my critical values is just about the only thing I would do on that calculator, or do on the table. Everything else I'm going to run on a calculator. So I do like to use the table to find my critical values. Yes?
That'd probably give us everything.
They give you formula, so this is actually what they give you right here. So formula sheet, right? You've seen this formula sheet a lot. No, this is the z-score table. You don't need that. And then here's t, and then here's even chi-squared. You don't need that. T is the only one I would use. So one thing I do want to point out really quickly. So notice on the left-hand side over here is my degrees of freedom, and here's my tail probability. Didn't we just say our tail was 0.025? And so here's where we're looking with what degrees of freedom. 29. Okay, so two things I do want to point out continuing from that. That's the same thing, 95% confidence level had a tail area of 0.025. The other thing is, what's happening to these t-values as we get higher degrees of freedom?
They get lower.
They get lower until they approach,
Like the true Z.
well, the z values, right? And notice that's when the degrees of freedom is infinity. So you remember how I told you all that bottom row is our z? It's because the degrees of freedom is infinity, and so that's our z-scores right there. But that's the idea, is as my degrees of freedom goes up, so as the sample size goes up, our spread is going down. Like we're going to have lower variability in S, so we're able to use a smaller critical value. That's it. Huh? What do you not like about it? You don't like the idea of infinity? Sorry, it exists. You probably really won't like the fact that there's multiple types of infinity.
Oh,
Multiple dimensions of infinity.
oh, I
I
know.
like there's infinite numbers between 0 and 1.
There are more numbers between 0 and 1 than there are from 1 to infinity. There's also more numbers between 0 and 1 than there are from negative infinity to infinity as counting by the integers. That's what I should have said. Yep.
Is the Earth flat?
Yeah.
Don't worry about it. I just said there's multiple types of infinity. Yes?
Okay, so it's 0.025 because if you add this together, that's 0.5.
0.05, yeah.
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 And that's what we need.
And then that plus the 0.95 is my 1.
Yeah.
Okay. But yeah, that's why the confidence level at 95% is the same as the tail area of 0.025.
Okay.
Yep. Alright, but again, there we go. Yeah, don't worry about the infinities unless you want to nerd out after class. That does not impact statistics. Alright, so margin of error. So how am I going to calculate this margin of error again?
With precision.
Stat. Oh.
No, just the margin of error. So we are going to do this by hand here.
It's your T value.
So the critical value, which is
The T.
t times the
Margin of error. I mean the critical error. Standard error.
standard error. And what is my standard error in this case?
Not sure.
Is
Is it 0.08 divided by square root of 30?
So the s divided by the square root of n. So 2.045 times 0.08 divided by square root of what? 30.
Oh, wait.
Sample size, right?
Oh, never mind.
Be careful and please do notice the difference between n and degrees of freedom. Okay? So we do use n in that standard error formula and they tell us that. Okay? What I now want you to do is work 11 through 13 within your small group, then we'll come back together, talk about it, and smooth. And so work with your small group, 11 through 13, we'll come back together in less than 10 minutes.
Oh. This is so nice.
It's just three numbers.
Yeah,
Yeah,
we
like my little
Hey Star, have you finished 11 through 13 before you start talking about that?
Calculate the 95 confidence interval using the weight estimate plus or minus margin of error. What is that? Yes. Interval. Yeah, so the point estimate is.
Again, you don't have to memorize it. You need to indicate your interval is capturing the true mean weight. So with 95% confidence, the true mean weight of Oreos is captured by the interval 11.16 to 11.22. You can flip it around. You just have to have that interval capturing the parameter. Yes, Andrew.
We are 95% confident this year.
You can say that as well. I am 90. I always thought, like, if you look in the textbook and a lot of other places, they always do we, and I'm like, what we is this? Is this the royal we? Like, I am 95% confident. Like, they do that. Trust me, like, I get it. They say it all the time, and I'm like, why? So you've seen me do it. They do it on AP Classroom?
Yes,
Yeah, and I'm like, why? I don't get it. All right, so here's what I want us to do, though. Number 13, a specific formula. So remember, my general formula is a stat plus or minus a critical value times the standard error. So what's the specific formula for confidence interval? for a population mean?
X bar plus or minus T over, and then times, standard,
What?
standard deviation over N squared or whatever it is.
There's my confidence interval for a population mean. It starts with X bar, the point estimate in the middle, then you add and subtract the critical value. Just remember standard error of X bar is S divided by root N. Is that what you're gonna ask?
So it's,
Divided by root N. Remember, that's straight off this formula sheet.
oh,
So when I look at means, and so we do need to recognize we're looking at a different place nowadays, looking at means, but there's my standard error up here. The standard error of X bar, S divided by root N.
I have a
Go for it.
question.
you know how, like, for the interval on 11, you wrote like 4 decimal places? in it?
Yeah, you don't need to do all that.
But, so if I do that and then I round it a little in the.
Interpretation, that's fine. Yeah. All right. Now, I live in the 21st century, though.
You do.
I do. So, how often do you think that I actually take the time to do my statistic plus or minus my margin of error? Never. So let's learn how to do this, okay? Now, here's the calculator. I'm going to cover this up so you can see it, and we're going to get into the rest of this stuff. All right. Any guesses what I'm going to do to menu? Okay. Then
6.
statistics,
7, stat test.
stat test.
6, 7.
Okay, so which type of statistics test am I doing?
A T. A T test.
T-test. Yeah. Notice we're not using a Z-test, we're not doing proportions, we're doing a T-test. Actually, whoa.
No, that's not right, because data input method?
Well, there's that, but we're doing a stat test?
No.
No, we're doing an interval.
No, we're doing
Oh yeah, we're doing a confidence interval, guys.
Ian, that was you.
You agree with me.
No,
Okay.
I didn't.
Confidence intervals. I agreed with you until I started to think about it, then I was like, hold up a second.
You
What type of inference procedure? T interval number 2.
Creepy shit.
Okay, so this is what you need to be aware of. So right here,
Welcome to
this is the question you have to ask yourself. Do you, hey pause for a second, I need you to think about this. Do you have raw data or do you have statistics? You have statistics. If you have raw data, the individual data values, you can just use that variable and put in raw data. Now don't do this, but notice if I hit data, you see how it asks for a list? It asks for a list from the list and spreadsheets page. So you can just type out the variable. So you remember how we put data values in list and spreadsheets? You can just do the list right there, okay? But we're not doing all that. We're doing stats. Yeah, what is my X bar?
30. Wait.
What?
About 11.19 was X bar. Now, Madeline, because you did this earlier, what do you have to be careful of?
Just put X, not X bar, standard deviation.
Well, this is S. Notice that is not, yeah, so this is not standard error right here. This is not S sub X bar. It's just S sub X. That is just the standard deviation of the sample, not a sampling distribution.
So 0.0.
Huh? Well, what's sigma? We don't have sigma. Okay, look. If we're doing our formula, I don't know what just happened there. Guys, the standard error of the sample means is the sample standard deviation divided by the square root of n. Notice we don't have S sub X bar. I don't ever write it, but technically this is S sub X, the standard deviation of the sample. Okay?
So we can't use that.
No, it's again
0.08. We don't have sigma, we have S. And what was my sample size?
30.
95% confidence level. Those numbers look familiar.
No.
Wait.
My
What's your standard deviation? 0.08.
It's really good.
Wasn't that what we had originally?
Yes.
That's my whole point.
Maybe I'll
Was
watch
that you don't do 0.08
Watch
divided by
Desperate
30. It's not the
Housewives.
standard error.
No.
It's just the standard
Watch
deviation.
it.
Okay.
Very
Please notice, hey guys, this calculator spits out a lot of important stuff. We have our margin of error. It tells me my degrees of freedom, and all those fun things, okay? So it tells me all of that information. Now, we already had all that. I know we probably haven't gotten a chance to look at 14, but I want to get to the notes. According to Nabisco, the average weight of an Oreo cookie is 11.33 grams. Does our interval provide convincing evidence that the true average weight is different than 11.33?
No, we reject the null.
Yeah.
What?
Wait, what are the intervals to intervals?
What are you talking
We
about?
have it.
Okay,
What is it?
so,
Dude, look at your paper.
alright, let's rephrase this. Our claim is that, not our claim, Nabisco's claim is that mu is equal to what? 11.3.
What?
I was saying, remember, they claim that it's 11.33. Our interval was 11.22.
1601.
Was,
To
did not capture
11.22.
that.
2.
Huh?
It's the same.
2199, 11.22 is fine. So, do we have convincing evidence the true average weight is different than this?
Yeah.
No. I mean, you have some because it's not within.
We don't have some.
You have
We have convincing evidence. Because what is this? These are all
value.
plausible values.
Not in there.
It is not in there.
So,
I know.
11.33 is
Not
not plausible.
That's the one thing I know.
Okay? So,
Specific out.
11.33 is not a plausible value, so we would reject their claim. We have convincing evidence the weight is not 11.33. Yes.
Do I have to write the interval for a question like this, like again?
Well, no.
Like, I was just gonna say.
It's not gonna hurt.
Excluded in the-
I would say, yeah, if you've already got the interval in the previous part, I would just say that 11.33 is not captured by the interval, so it is not plausible. Is probably what I would say. Now, I do want to ask this question. Okay, so that's the answer you would want to have there. 11.33 is not captured by the interval, so it's not plausible. What if Nabisco claims that U is equal to 11.2?
Very plausible.
Yes.
Do I have convincing evidence
Yes, beyond a shadow of a doubt.
No, I love you.
U equals 11.2?
Ian, you just made me mad.
Since you're all the way with this.
Hey, you need to pay attention to this. There's a reason I'm asking this question. Do I have, if this was the interval and this was their claim,
Yes, it captures.
do I have convincing evidence that mu is equal to
It is a
11.2?
plausible
Yes.
It is a what type of value?
Plausible value.
It's a plausible value. So, we have convincing evidence that mu is 11.2?
No.
No,
It's only plausible. It could be, but do we know mu is 11.2?
No.
No, remember guys,
Never know anything.
well, it's not that we never know anything, we never prove the null. That's essentially what that is. Here's the thing, that's plausible, but is it the only plausible value?
No, there's 8 more.
There's infinity other values.
There's infinity.
There's infinitely many values.
So we have.
So,
proof that
and that's
it's
the
not.
thing, it's, have we proven that mu is 11.2? No. Is there evidence that mu is 11.2? Sure, but it's not convincing. Okay, I need y'all to understand. Once again, if it was this, that's not even plausible.
Right.
So I would reject that. If it was this, it is plausible. I haven't proven that it is. I would just fail to reject this one.
FDR.
Okay?
Always so negative in stats. Like, it's this, and you're like, I can't prove that it's not.
I know. Yeah.
Can't prove that
If
it's
you
not.
put an interval, and infinity is infinity,
Yeah.
there's no interval because there's still so many options.
Well, but that's again why we can't
Infinity
prove
less
this is
of
it.
infinity.
There's infinitely many options inside of here. I can't prove it's this. I just can't disprove it.
Is that even real?
You
Prove
can't just
that's
not just
real?
prove
Stats is not real.
I can disprove that because that's not plausible.
But it's possible.
It is possible, but not plausible. Okay, so conditions. Yeah, so we're gonna stop sweating that detail. All right. Conditions here.
It's like when you open
So what conditions do we have for these inference procedures?
C
CLT.
So we've gotta have random,
10%.
okay? Random sample or
Slash,
Assignment.
assignment, okay? Remember they have different goals, okay? What was the other one?
The CLT.
10%.
10%.
Let me come back to that one. 10% condition. Now, remember, you don't always have to have that, but if you're sampling without replacement.
What is the CIF?
If.
But the
Oh,
point
dear.
is,
That's so mean.
Okay.
watch.
Now, I need you to be careful because you don't have to have the central limit theorem. The sampling distribution needs to be of x bar needs to be what?
Approximately normal. Large enough.
Okay. So here's what we do. It could be CLT, right? Which would be a large sample. But even if you, and that's n is greater than or equal to 30, the central limit theorem, large enough sample. But you don't always have to have a large sample because when else will the sampling distribution of x bar be approximately normal? Or if the parent function is normal. So this is usually called the large or normal condition. Because if the sample is large, sample size is large enough, or if the population was approximately normal, the sampling distribution is approximately normal. So you have to keep that in mind. There's the central limit theorem. The sample size is large enough, or the population was approximately normal. That looks like a terrible idea, Ethan. That was a choice. How blind are you,
I
Star?
have the worst vision in here.
No.
Yes. Nothing like an AP stats class for people to start arguing about who has the worst
It's
vision.
so bad.
I just
have
realized,
negative
like,
7.25.
we all have glasses except for Madeline.
Madeline, you want to be
And so-
different.
And that's why
She's always has one.
Oh.
You
So
don't
do you
let
have
her
glasses?
put you, she's wearing contacts.
My glasses for like a whole week.
Kenny, where's your glasses?
Let's be
At
honest.
home?
Mr. Anderson.
You actually.
We all have glasses.
Oh my God,
Let's go.
You need
Mr. Anderson has
glasses.
glasses.
Yeah. I just always wear contacts.
You're getting old.
Oh, wait, no, I don't.
No,
Contact made me cry.
I've always needed glasses. Alright, critical values. Okay, so what critical value do we need?
T star.
T star, for, with, what helps us determine the correct T star?
The table.
The degrees of freedom equal to n minus 1, right.
That's
So, and I would probably add this detail in here. We need a little larger critical value to make the margin of error larger and get the correct capture rate. Okay, so like that's the big idea here is you need a critical value that's a little bit larger to have the right capture rate.
Mr. House is not scaling with the grades. No, he said star about it.
Yo, how is that gonna help anybody right now, Star? Don't talk about that. It's gonna make people more sad.
No, I'm already upset
To
about it.
capture
I gotta everybody
the,
using
the,
And get the correct capture rate.
oh, it's right there.
Yeah, to make the margin of error larger and get the correct capture rate.
Classroom. Can you stop talking about? Dude, chemistry is actually
I'm
like.
about to show you that.
Hey, guys.
What is it? What is that? You got these things.
Excuse me.
You're in pain. It's insane.
Yeah.
Bless you.
Please stop.
I had to line them in. The
Yeah.
star was the.
In. Can we say a little bit stronger?
Guys, we can watch the party at
Pot of
5.
boiling oil. I'm not a woman.
Mr. Anderson, do you watch Wicked? Or
And if
has
he drowns, he's
I don't
not
know.
a key. And if he gets out, he's a
You
win.
haven't seen Wicked?
I'm not.
Star,
What?
What?
What is the problem?
Hey,
Yeah, lots of-
sorry, I was wondering if I was supposed to bring it up here or not, so I want to go ahead and talk about this. So, two things. One, if you look at your T distribution sheet, notice how it only goes by ones up to what, 30?
Yes.
So let's say that your degrees of freedom was maybe 34. It's not on that table.
Can't you just put it in?
So one, you can use a calculator to get it, or two, just round down degrees of freedom if it is not,
So we
On
could
the
just say
table.
30?
but you can always use a calculator. But that means if my degrees of freedom is 34, I'm gonna round it down to what? 30.
What if it was like 39?
You would still round it down, because you need to make the interval wide enough to have the right capture rate. So you round it down. So the degrees of freedom is 38, you're still gonna round it down to 30.
There's a lot.
If you go to a higher degrees of freedom, then it will not have the right capture rate.
What if it's not?
Alright. The other thing is this, and this is actually what I couldn't remember if I was supposed to talk about yet or not. This is gonna sound bizarre, but, not bizarre. How often do you know if the population is normal?
Not very.
Not very
if it tells
often.
you.
Only if it tells you. Are you always gonna have a sample size of 30 or greater?
No.
No. The last thing that works here for this large or normal condition to believe this, if the sample doesn't show strong skewness, then you can also do normality. Okay? So this large enough or normal condition can also be satisfied this way. So no, it's not just making stuff up. If you look here, okay, so going back to the pennies, what kind of population distribution did it have?
sample.
No, what type of population? It was very skewed, right? Remember, it was a very skewed distribution, and then our sample was also very what? Skewed. If your sample is roughly symmetric without strong skewness, it is believable that the sampling distribution is approximately normal, is what we say. So as long as there's not strong skewness like this, we don't think our population came from, or the population is not skewed. Okay? And so that's something we'll have to play with, but that's all it is. Okay? So if the sample doesn't show strong skewness, we'll run with the test as well. All right. Okay. And don't forget, when do we use Z critical values?
When we're given the
proportion?
When we're given proportions. Don't forget, we use Z as our critical value when we're given proportions. We use T when we have means.
none.
Means, dog. Okay. Everybody have these quick notes down?
Well, yes.
Well, yeah.
No,
No, for real?
No.
What do you?
Why'd we go back?
I hit the button. Okay. All right. So, I do want to remind you, big critical value or big confidence interval concepts, how to interpret, all that stuff, exactly the same. Do you have to worry about T for your test tomorrow?
No.
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 No. T is only for what?
Means.
Means. Tomorrow is all about proportions
Confidence intervals.
and hypothesis test. Okay, this shouldn't take too long. I do want you to just check your understanding. Number one, use the table B, and then if possible, check your answer with technology. So find the critical value for a 98% confidence interval and a random sample of 26 observations, 99% from a simple random sample of 85. So pull out your table, look for those critical values.
So would I have 25?
I'll probably like 6 years older.
Girl.
Okay. Five minus one. Yes. If you say that to me again, I'm gonna tell you that.
I said something.
Oh,
Yes.
what a
I
threat.
am texting the
Mr.
Mr. Kim.
Oh, wait.
Oh, no.
So is it T? Oh, no, we're supposed to do a confidence interval. Yeah, we're supposed to do an interval for both of those.
Rich and mysterious. He's always just like walking around like he knows something no one else knows.
2.485.
I hate everybody.
X
25.
Wait,
Look at it go.
are we doing just one?
Wait,
And your mom.
No,
Too.
I need to do it. I need to do it now.
They put these similar in goat status.
What's up, Lee?
Wait, you don't even know what I was
I did not put down.
You would knock it down to 80, correct?
Wait, wait, I'm confused, what are we doing? We're not finding.
Okay.
It said.
Wait, chill out, bro.
Hold the phone.
You hold the phone.
Like,
Oh, make it
I forgot how to find the T. Ah.
Fall asleep.
I remember.
To do it with fun.
That's asking for
Alright, so my critical values off the table are already on the board, okay?
I'm good.
So those are based on the table, not based on the calculator, okay? Do I need to talk about either?
Oh, do we supposed to do it?
I was going to show on the calculator as well. Okay, so on the calculator, right, menu, probability, what do I need to hit?
Inverse versus not T. Sorry, T.
Yeah, I was like, I want a T critical value. Alright, so 98% confidence level, what area?
0.05.
That's 0.025. 0.1.
0.01 for a 98% confidence
Oh, I
level?
thought we were on the second one.
No. Degrees of freedom was 25. Is that the same answer? Negative 2.485? Or
Yeah.
2.8485? Okay.
No, it's not. What? I didn't get that.
What did you get?
I got 2.479.
Because you gotta go one less.
Did you do degrees of freedom as n minus 1? Or did you do degrees of freedom of 26?
I didn't just calculate.
It's on the sheet.
I got it wrong.
But I think you did too high of degrees of freedom. I think you did a degrees of freedom of 26.
I did.
But it needs to be 25. Alright. Do notice, this is again why I like the calculators. I can get more precise with the second one. It is 0.005. And the degrees of freedom would be 84. So notice this will not be exactly the same as what the calculator spits out. But this would be a more precise critical value. Notice, is that very close? Sure, but notice, is it bigger or smaller? Smaller because it's a higher degrees of freedom. I was able to do a degrees of freedom of 84, not 80. Okay? So, determine if conditions have been met. Is it a random sample?
Yes.
Yes. Do we satisfy the 10% condition? Yes. Is 1,640 less than 10% of all adults? Yes. Do I satisfy the large enough or normal condition? Because that's a wicked skewed distribution.
Well, it's 1,600 adults.
It's only one
I
sample.
would say, remember, there's a few options. Either the population is approximately normal. That is, we don't know that. The sample doesn't show strong what?
Evidence.
Skewness. Does our sample show strong skewness?
Yeah.
Yes. Or central limit theorem. N is large enough. N is 1640, so large enough for CLT. So, do we satisfy all three conditions? Yes.
Mm-hmm.
Yes.
Guys, remember, it just has to be one of these for the sampling distribution
Oh, wow.
to be approximately normal. We need to recognize, you just have to satisfy one of those. If you satisfy the central limit theorem, done. You only have to care about the other ones if you don't satisfy central limit theorem. Okay. Only have a few minutes. Oh yeah, we don't, I guess it kind of works out that we don't have this. Do this for me tonight.
I didn't tell you my screen time.
No, don't tell me the screen time right now.
It's on my iPad.
Oh. Tonight, send me your screen time for today. I'll convert it to minutes and then I'll put it into the StatsMedic applet.
Wait,
Because I accidentally forgot to do two-sided. Notice it's all one-sided on that. So yeah, please notice the homework, I messed up and I made it one-sided instead of two-sided. Yes?
We're talking about people use because of so they're doing copies under
Hold on, start. I can't hear him. Other people are talking. Say again, Charlie.
because of the folks they go there and they're estimating the actual proportion of actual.
So we would have some biased data, but we'll just base it on this group. And like, this is still biased in comparison to the rest of the school. Don't sweat that detail. Just send me the data for U12, and we'll run our confidence interval tomorrow after the test. Okay? So I need your data. Yes, Steve. Huh? Yes, I want combined. Yeah. So guys, send me all your screen time for, let's do it for yesterday so that it's already done. If you can't see yesterday's screen time, look it up for today.
I slept with my phone on.
35
So my screen time's gonna be.
Yesterday?
Yeah, I'm never on my
I felt like I was
Well, but you also have your
last night.
iPad.
I was like getting so much
I'm not
hot
never on
flashes.
my phone.
Why
Listen.
Listen, when I did, hey guys, I just need y'all to hear me clearly on this. When I did this last year, it was on a Monday, and I kid you not that Peter went, oh yeah, I had like 20 hours of screen time yesterday. And I'm like, Peter, dog, how? Because I was up really late, and then and I'm like, dude. And I kid you not, also, he said that was on only one device, because he had like 2 or 3 screens going at once. And I'm like,
Oh, I hear
Peter,
that.
how?
My iPad, my computer barely.
So trust me, I've heard worse, okay?
Peter's like a different breed.
Huh? Give me all your screen time combined. So guys, email me tonight all of your screen time combined.
So,
Even on my
Say again.
iPad.
For yesterday, just yesterday.
Mr. Anderson, cheese!
Do I like also?
Yes, you're going to AP. You're going to AP stats yearbook.
Aw, thanks.
Okay.
Only 2 minutes of your last time at Hillcrest.
Wait, are you coming back at any point?
No.
No, he's out.
No! Why?
Where are you going?
That's biased.
What do you mean?
Okay, so me
He's
and
getting
Cameron,
slimed according to stream.
True.
me and Cameron came up with something for Moon Alpha Data, and you have to have it because it's a mystery.
Mr. Kenny Merchant apparently.
Wait, oh well, some of my classmates will be here next semester, so if there's a form for merch, I'll actually buy Mr.
Well,
merch.
we were gonna have a Kenny Christmas ornament, but you can get it late.
Okay,
Next year.
that works for me.
Mr. Anderson, what's the email?
What's my email?
Yes.
Yes.
Sophie,
Hard. Okay, yeah, so don't tell you screen time.
don't do that. I don't know why.
It's okay. It's okay. Yes, you have to watch Welcome to Dairy.
I'd probably
Go with that.
Send that, Tony!
so I can get followers.
My brain at lunch.
Okay. Yes, you can do it.
That's a folder count.
Like 800 or something.
Yeah, they talk about